Okay, we're in the back realm of science in the storage area here. We're going to talk about Newton's second law. We spent a long time talking about inertia, Newton's first law, what forces are, and we want to get this quick video in of Newton's second law, and that is relating to acceleration and how that affects motion, right? So we have these forces. The main idea here is that these forces could be balanced or unbalanced, right? You could have them in equilibrium, the net force would be zero, or they could be unbalanced. So when they're unbalanced, you get an acceleration. That's why sometimes you have forces like a tug of war happening and the rope isn't going anywhere because the tension forces are equal in both directions. There's still a force applied on it, but it's balanced or in equilibrium. So Newton's second law tells us how acceleration affects force and mass, and it's famously known as F equals ma. So Newton's second law tells us that the net force acting on an object causes an object to accelerate in the direction of that force. Remember, because forces are vectors, they have a direction. Acceleration is a vector, has a direction, right? And it's the change in velocity, which velocity has direction. So Newton's second law explicitly says that the force or the net force acting on an object causes the object to accelerate, and it accelerates in the direction of that force. So we get the equations here, A equals F over M and F equals MA. Most people are familiar with F equals MA, but it comes from A equals F divided by M. More on that relationship later. Let's take a look at an example here. The acceleration of an object depends on the object's mass, or it also depends on the strength of the outside force acting on it. So let's say you have a golfer that applies a force to a ball with the club. This force could be written proportionally as the result of the product of M times A. But as it turns out, the mass was a lot less than the acceleration. So your end product is this force, right? Or let's say you have a force that's sort of large and a mass that's sort of small, you get a huge acceleration. Compare the same force if the golfer tries to hit a truck. The truck has a much, much larger mass than the golf ball. So if you exert the same force on a larger mass, it's going to have a smaller acceleration. There's a proportion involved in this. So just a quick reminder that the force is the thing that's causing the acceleration. So the force from F equals ma, it has to be the net force when we're talking about this. We're going to keep it simple and just talk about, one force at a time. But the net force would be the combination of the forces acting on the object. Remember our units. Forces are measured in newtons. Newtons are kilograms times meters per second squared. So it's the amount of force that it takes to accelerate 1 kilogram to an acceleration of 1 meters per second squared. So an object is only going to accelerate if there's an unbalanced net force acting on it. I have to repeat this. We have to sort of think of acceleration is the result of unbalanced forces, okay? And that the direction of the acceleration is the direction of the net force. So imagine an object in free fall. If you drop your book, the acceleration due to gravity, we all learned about that, is always pointed downward. Well, the force of gravity will be pointed downward direction as well. So an object will only accelerate if it has an unbalanced net force. So if the book is in free fall, okay, and the force of gravity is overcoming the air friction or the drag, then that's an unbalanced force. Let's take that same book and place it on the table. The book on the table does have a weight to it, or a force of gravity, but it also has this supporting normal force that's pushing it up in the opposite direction. So there is no acceleration on that. So an object will only accelerate if the net force is unbalanced. So here's a couple of different scenarios, a couple of different pathways that we could go when we have unbalanced forces. According to Newton's second law here, when the forces are unbalanced, there is an acceleration. 2, the acceleration depends directly upon the net force. Okay, so if you have a tug of war, if tension going left and tension going right, those forces are competing. Well, if one force overcomes the other or is greater, you have an unbalanced force. So it's going to accelerate in the direction of that unbalanced force. And also, according to Newton's second law, the acceleration depends inversely upon the object's mass. So I'm going to talk a little bit about the sort of algebraic relationship between F equals ma and how that affects the outcomes. So if you double the net force, you double the acceleration. If you double the net force, you double the acceleration. So F equals ma. If you double the net force, you double the acceleration. Now, so long as mass is the same, right? So we were going to assume mass was constant. So if you have an object and you double its mass, you end up cutting the acceleration in half or dividing it by a factor of 2. And again, this is if your force is constant. So what could we call that? What could we label that? There's, things that affect acceleration in the equation F equals ma. On the left side here, I've got force written down. So how does force affect acceleration? Well, acceleration is directly proportional to force. If you increase the force, you increase the acceleration. On the other hand, mass, on my right side, acceleration is inversely proportional to mass. So if you increase the mass, you're actually going to decrease the acceleration. In law number 2, we said that the acceleration of the object depends on the object's mass and the strength of the outside force acting on it. F equals ma. So if the forces acting on them are equal, who is going to accelerate more? Let's take a look at an example here. There was a show called Fat Albert when I was a kid, and he had a buddy named Rudy. And I used to watch this, and my childhood was awesome because of it. So let's take a look and compare Rudy. He's a little smaller. Fat Albert is a little large around the middle. And if the forces acting on both of them are equal, who should accelerate more? I think common sense tells us, and also Newton's law, that Fat Albert is not going to accelerate as much as Rudy. Fat Albert has a lot more mass. Okay, so say we have an example of a cow. Let's calculate the acceleration acting on this cow. Now, what is the acceleration of the cow if it's 500 kilograms and it's pushed with a force of 1,500 newtons? So you would use your formula, identify that the force was given and the mass was given, find acceleration. You can answer that now. Here's some other practice for us that we can do. What's the acceleration on a 300 kilogram walrus being pulled by a force of 1,000 newtons? What's the acceleration of a 300 kilogram walrus being pulled by a force of 1,000 newtons? Don't worry about sig figs. Okay, now I'm going to take it a little step further. What if you already knew acceleration? Let's say you have a rocket. The rocket's mass is 30,000 kilograms, and it's accelerating at 10 meters per second squared. How much force is acting on the rocket? Here are 3 more problems that I would like you guys to practice with. The numbers are simple so you can understand the concept. 90 kilogram person is pushed with a force of 100 newtons. What's her acceleration? A cannonball shot out of a cannon with an acceleration of 10 meters per second. This time the mass is 100 kilograms. How much force does the cannon fire with? Find the mass of a cart if a horse pulls it with a force of 500 newtons. The acceleration is 0.5 meters per second squared. Okay. It's important that we continue to stress that forces don't cause motion. Forces cause accelerations. Forces cause accelerations. Accelerations are the things that we say cause motion. It's the accelerations that cause motion. This is your change in velocity. That could be the magnitude of the speed or the direction. If that changes, you get an acceleration. Like we said earlier, you have a tug of war. It's not going anywhere. Doesn't mean there's not force on it. Your book sitting on your table, that has forces acting on it. It doesn't have to be moving. And likewise, you could have an object that's moving at a constant velocity. Forces are acting on it, but the net force is balanced. The net force is 0. All right. In this section, I want to talk about calculating weight. Weight is a force. So force is mass times acceleration. On Earth, we know that the acceleration due to gravity was negative 9.8 meters per second squared. Apologize for not having the negative sign in there. And then masses are in kilograms. You can do this with your own weight if you knew how massive you were in kilograms. Let's do one more practice problem. Let's say Joe pushes a 100 kilogram box so that it accelerates 4 meters per second. How much force is Joe applying to that box? So you're given a mass, you're given an acceleration, find the force. Let's get right here, and we'll see you in class.